3, 2. Hello, Ellie. Hello, Teresa. And thanks for joining me. Let's see if I can get the other two here as well. And sorry I'm a couple minutes late. We are going to talk today about light. So we'll try and show a little light on the subject. We'll do a little light physics today. We're going to start out with that, which we had last time, but it's still worth looking at. Well, Kevin, you can't see it. You probably still can't see it. I'll get you closer in a second. Don't worry. Okay, there's somebody else joining us. Who is that? I got a third person. I like it. 75%. It's Zach. Hello, Zach. Thank you, everybody, for joining us. Good. One more and then we're there. But let's go ahead and review a little bit from last time, okay? I think we drew some of this, so I won't redraw it. But let's kind of remind ourselves what's going on with light. It's an electromagnetic wave. We'll study electromagnetic waves later in the course. But for now, we just need to know it's a transverse wave, okay? And for that transverse waves, if they're really big, I'm going to zoom you in now, ready? If they're really big, they're here, radio waves. Look at this, 3 times 10 to the 4th meters. That's like, what, 3 kilometers, 30 kilometers? Anyway, radio waves can really be really big. Luckily, they don't hurt us, right? They're going through us all the time. Well, interestingly enough, they got a really big wavelength, but they've got a shorter frequency. Let me read some frequency numbers to you. Out here is 10 to the 20th, 10 to the 14th, 10 to the 10th. So these are 10 to the 4th, and that would be still a lot. It'd be like 10,000 hitting you every second. Radio waves, okay? Light's so fast, even the big ones are still moving the same fast speed. So a lot of crests would hit you every second. Now let's go to the other end. Gamma rays. Okay, so gamma rays, man, these suckers are tiny. 3 times 10 to the negative 12 meters, so less than an atom long for the whole wave, okay? Really, really tiny. And so they come really frequently at you. So this is 10 to the 20th, but they go beyond there, 10 to the 22nd, 10 to the 24th power per second. So man, oh man, oh man. Lots and lots of gamma rays. We also said last time that the greater the frequency, the more frequently they hit you, the more energy they've got. And that's why gamma rays can be very deadly. They carry a lot of energy with them. Radio waves, AM, FM radio, don't worry about it. Not such a big deal. Okay, and Sophia, you out there? I see 4 people. I know sometimes you have problems, and Sophie, being able to communicate, but I'll just, hopefully that's you, and I'll say hello. So let's learn some stuff about light today. For starters, we know it's really fast. And I know we had that number before. I think we talked about these other things, didn't we? Let's see. Microwaves, infrared, ultraviolet, X-rays. We kind of talked a bit about all those, didn't we? Just sort of chatting. We'll talk about some of those in more detail. Okay, but let's come back to that, okay? Cool. Yeah. Recall, light's really fast. C, the speed of light, which we studied in the Einstein unit, right, is 3.0 times 10 to the 8th meters per second. Well, the phrase that we need to learn about light that I'm sure you've heard before is a light year. Let's see if one of you know already. What is a light year? What is a light year? And would you say our Corona year is not a light year? Just kidding. Bad joke. 2020 was not a light year. 2021 has not been so light yet either. I know that. But what is an official light year in the physics meaning? I'll start you out, then you can fill in the blank. A light year is the distance You got the rest of that for me? Go ahead and fill it in. The distance what do you think? What about light? A light year. Well, it's been kind of quiet out there, unless there's just a big lag time today. But your responses should be moving at light speed through the computer, but I don't think it really does. Okay, the distance light travels in 1 year. Ta-da! Okay, like the nearest star is our sun, okay? Yeah, there you go. Thank you, Teresa. So the distance to our sun is, of course, oh, man, I'm not saying this very easily. Our sun, the light takes 8 minutes to get here, okay? Eight minutes for light to reach us. Moonlight is a lot closer. Remember, moonlight is not coming from the moon, gang. It's just what reflected off of the moon, right? It's coming from the sun, hits the moon, and then we see it. Moonlight takes about 3 seconds to reach us, which is kind of cool. So when you see the moon, you're seeing it from 3 seconds earlier, if you think about that. You're not really looking at it. You're looking at it as it looked 3 seconds ago. If you glance up at the sun, that's the way the sun looked 8 minutes ago. Well, our next star, Alpha Centauri, I think it's called. I might have that wrong. Closest next star is measured in light years because it's so flippin' far away. So you know what? I'm just going to get that real quick because for grins, I'm going to put in the number in my notes too. Closest star in light years. Here we go. Don't you love the internet? That's what I thought. Okay, it's called Proxima Centauri. I knew that because it's Proxima, it's close to us. And it's 4.2 light years away. Where'd you guys go? There you are. Okay, so so the nearest star is 4.2 light years away. Let's see how far that is. Light years away. And it's called Proxima Centauri, if you want to know. Centauri, I guess is how we'd say it in German, huh? I knew that, but I'm going to write it down here in my little notes for future reference. Okay, sorry about that, but we got to do these things sometimes. Let's figure out what a light year is. You ready? Here we go. So, how far is a light year? All right, so then we'll do 4.2 times that, okay? So a light year. So it should come out into meters. In meters. Well, we start out kind of in meters. It's meters per second. 3.0 times 10 to the 8th meters per second. We just got to kind of get rid of seconds. So let's kind of do that. Let's go from seconds to hours. What's our relation there, gang? How many seconds are in an hour? Let's see if you can do the math here. So I know you're waking up here at 11:44. How many seconds in an hour? How many seconds in an hour? I hope all of you are there and not off brushing your teeth or something. Ah, Zach's there, and so is Ellie. Thank you. Okay, good. 3,600. 60 times 60. Yeah, good. Then we're going to go what? We're going to go hours to days. Well, we know that one, right? And then we're going to go days to years. Did I put that right? That looks wrong, doesn't it? Let's put days up here. 1 year. Okay, 1 year what? 365 days. And then 1 day, 24 hours. And could I ask you to do some calculating? So pull out your handy dandy calculator. And can you do all these maybe first? Boom times boom times boom. And then multiply that times maybe in parentheses 3 times 10 to the 8th power. Let me know what you get. Let's see if we get the same thing. Okay? So boom, 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 and then times 3 times 10 to the 8th. It's going to be a big number. I'm going to make a little space down below. All right, let me know what you get when you get there. If you don't have a calculator, pull one up from the internet and please punch it in. See what you get. See if we can agree on our answer. And I'm going to put the answer down here. And let's see, while you guys are doing that, I'm going to cross out some labels. Days goes, hours goes, seconds goes. So I'm going to get meters per year. That's what I want. Meters per year. Okay, still waiting on you, gang. My wonderful 4 total physicers. So find your calculator. Let's see what you get. Boom, 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 times boom. Thank you, Ellie. I'm going to write it and let's check and see if others get the same thing. So it's got 9.5 times 10 to the 15th power. And then she's got a good label on it, meters per years. That's what I came up with as well. Let's see if others get the same thing. That's for 1 light year. So for Proxima Centauri, the star, is 4.2 times that thing. It's really far away. If we do that as a number, and Zach got 9.4, but still the same thing. No, I got to round it. Okay. And Teresa got that too. Okay, thank you. Thanks everybody for doing it. Appreciate it. Appreciate the participation. So, just for grins, I'm going to do this. So I got 9. So there's 15 powers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I got, there's thousands, millions, billions, trillions. Wow. So it's 950 trillion miles away. Did I get it right? Thousands, millions, billions, trillions. Not miles, meters. Holy cannoli. And that's only 1. And then 4.2 times that is the nearest star. I want to not just impress you with the size of that number, 950 trillion meters, but also the idea that between us and the next star is nothing. There's a lot of nothing out in outer space. We're lucky. We're really lucky to be on something, a nice blue planet. There's a lot of nothing out there. Wow. And that's the nearest one. So aside from that and a few planets close to us, there's even more nothing in all other directions. You know what I'm saying? Isn't that crazy? It's just a whole lot of nothing. Okay. I don't want to depress you. I just want to make you relatively happy that you're at a good spot here. Earth's a lot better than halfway to Proxima Centauri, right? In case you're hitching a ride. Good. Okay. There's 2 theories of light, and we're going to study both of them. Okay? 2 theories of light. And maybe you know one or the other. I don't know. Well, you could probably guess. One of them is light is a wave, and because we've been studying waves, right? Well, the other one is that light is a what? I'll say light is a what? If it's not a wave, especially early scientists believed it wasn't a wave, it was a instead. See if somebody knows. What's the other theory? We often think of light just being a wave, but really it can also be this. It can be a particle. So you and I are going to study the particle theory for a little bit here today. And don't think it's some bogus theory. It actually works. And we often use it in science. We don't just use the wave theory, we use both. We'll see why that is. Okay, so under this theory, you ready? Light. Did someone know that for grins? I don't know. Light is made of particles called, and I know you've heard of this, especially if you're like me and you used to watch the Star Trek movies. Right? Captain, we're going to hit him with the So light is made of particles called, starts with a pH. Do you know it? What's the word? Light's made of particles called pH what? Yeah, thank you, Ellie. Photons. We've got to hit them with the photon torpedoes, Captain. Or whatever he used to say. Light particles called photons. So a photon, and I'm running out of room, so I'm going to go up and erase our light here. In light speed, I'm going to do it. Already hard. So a photon, think of it as like a little package of light, okay? To be a good theory, photons have to, well, particles of light have to go along with all the things you and I know about light already, okay? What does light contain, everybody? What does light contain? You're standing in the sunshine today. What does light contain? What does light contain? If you're standing in the sun, you know this. Well, what are you going to feel? You're standing in the sunshine. Bright sun. Light contains. Anybody got it? Energy, gang. You know that. Right, we're standing in the heat, exactly, a type of energy, right? So can that happen if light is a particle? Can a particle contain energy? Well, here we go. Let's say that's my photon. Well, a moving photon, yeah, we know that, gang. A moving particle could also contain energy. What sort of energy would that be? A moving particle. We learned we would call that energy. Energy. What would a moving particle contain? What sort of energy? What did we learn? In other words, yes, this theory works. The particle theory works because it could be a particle, or particles have energy. Thank you, Ellie. Thank you, Teresa. Kinetic. Ta-da. So again, what I'm trying to emphasize here is to be a good theory, it's got to work with what we know. So particles, can they contain energy? Yes, they would have kinetic energy, moving particles. All right. What can light do? Hint, mirror. What can light do? Light can, what can light do? Think mirror. What can light do? Thank you, Zach. Exactly, it can reflect. Well, Can a particle reflect? All right, think about it. If I throw a particle, especially if I can get rid of gravity, if I got a wall, if I throw a particle here at this wall, bang, bang, hey, it reflects. So yes, if I get rid of gravity and just have it bounce off a wall, well, we say things are bouncing. Think of like a tennis ball. Boom, 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 right? So yes, particles can reflect also. So we say, yup, the theory's working. Particles can bounce or reflect off surfaces. What else? Well, there's a quality of light that you and I have not studied yet, but we will. It's called refraction. Not reflection, but refraction. Refraction means light is slowing down. Well, we're going to study that another day. But think of this. Can a particle slow down? Well, it can. Take a tennis ball, a little mental experiment. You ready? Exactly. Reflect or bend, right, Teresa? Take a tennis ball, and now I want you to throw it right into a pool. When it hits the surface, here it comes. Boom. It's going to keep moving underwater, but won't it move? Here it goes. Boom. Won't it move slower and maybe at a different angle? Yes, light does the same thing. Light bends or refracts. And if I throw particles and they hit a new medium, what they're going through, they can also bend or refract. So my point is the particle theory also works for refraction. It does make sense. So I'm going to do just a little check here and say, check, light, and yes, particles can refract. F-R-A-C-T, refract. My point is the particle theory does work. And now let's go to the nitty-gritty, as they used to say, which means the guts of this thing. So I want us to figure out with the particle theory, how do we get different colors? Okay, so for particles, with particles, colors, if I could spell colors, colors are due to what? Okay, so here's my red particle. What do you suppose could be different about the blue particle? What could be different in the particle theory? So if that's my red particle, here it is moving. What could be different about the blue particle? They're going the same speed, right? The speed of light, so that won't be different. But what could I change about a blue particle that could make it be blue and not red? Can you guess? Here goes my red particle. Oh, there's my red photon. A blue photon? Yes, I agree they would have different amounts of energy, Ellie. Because why? What physical thing could I change about the photon to give it more or less energy? I could change the of the photon. Here's my red one. How could a blue one look different? How could a green one look different? And that's where my magic marker analogy doesn't really work very well. Maybe it's speed. No, Zach, the speed's the same. They're all going the speed of light. So I can't change the speed, but I could change what about, I can't change it here. Yeah, Ellie, the size. Or we could say the ma. I could change the, of the, so particle color, with particles, the colors are due to, well, I should write changes in. Changes in Somebody got it? Thank you, Teresa. Mass. Here's what I mean, okay? As an example. If it's a more massive photon, more massive is, oh, and I just threw it away because I got a, sorry, let me go get it. Luckily, my studio is not so big. It doesn't really take so long. More massive would be blue, a blue photon. Okay? Whereas for a lighter or less massive, lighter photon would be a red photon. So we can even think of it differently, okay? So there's a little red photon. And I'll write up above there, now that I threw it away, the more massive blue photon. So somehow the blue one's got more mass than the red one, okay? But they're both going the same speed, okay? Good. What about, and again, I'm out of room, so I got to go up here. Under this photon theory, right? This theory of light being a particle, what could account, or what accounts for light intensity? So again, light is made of particles. What could I change so I'm seeing a really intense red or a very, very dim red? What do you suppose I could change about the number of particles? How could I get light to be more intense? What could I do here? I could have what change about the situation? Or if I want a dim light, what could be hitting me? So if I see a really bright light under the particle theory, it could represent, well, not mass anymore. That was due, mass made it a different color. But let's say we're going to compare a bright red with a dim red or subdued red. What do you suppose would be different? Yeah, exactly, Ellie. Right, the number of particles. So what we think is going on is if it's a really bright red, here's you, okay? Looking this way, there's lots of particles coming your way, okay? Lots and lots and lots of them. Oh man, that's a bright red, okay? If it's a dim red, here's you again. There's just a few particles. Whoa, your eye got in the wrong spot there. There's just a few particles coming your way. So that's the thing, okay? So what accounts for light intensity? The number of particles. More particles, brighter, brighter. Good, Swelleroonie. So that's sort of light intensity, intensity. Let's go to the other theory. I think, let me see. Okay, another thing about light, it travels straight, and of course, particles could go straight, so that could work okay. Now, unfortunately, I'm not at school because there's a demo I'd love to show you. And it was called a single slit demo, and it goes like this. Or no, a double slit demo. Here's some light, and it goes through this slit, and it gets divided basically. Let's say it gets divided in two. And then the two sources of particles, the guys that believed in the particle theory, as we're talking like 100, 150 years ago, believed that it would just be a big mess on the other side. That when they went through, it'd be like, think of like a hose spraying through a slit. It'd just be a big splatter on the other side. But instead, they got a beautiful alternating pattern, which was called an interference pattern. So the people that believed the other theory had good evidence that light was also this. So let's go to theory number 2 now. So we called theory 1 the particle theory. We're going to now call theory 2 the light is a wave theory. Okay, we got to test our theory and see if it works with the same stuff. You know what I mean? Okay. Remember, we said light has energy. So my question to you is, can a wave have energy? Does our theory work for that, our new theory? By the way, we're talking about a wave like this type, transverse wave. Can a wave have energy? Yes, it can. Thank you, Ellie. It certainly. Think of the beach. They got a lot of energy, those waves, right? Sure. That definitely works. Check. Can waves reflect? Can waves reflect? Hint, have you ever heard an echo? Oh, yeah, waves can reflect. Think of sound reflecting off a wall, even if you're not even thinking of a light, even if you're not thinking of a spiegel, a mirror. But of course, all sorts of waves reflect. So definitely, can light reflect, or can waves reflect? Sure. We also know light can refract. Can waves refract? Now, we haven't studied this yet, but it turns out they can. Again, there's a demo I can't do. Okay. Um, so if I change what the wave's going through, for example, water going through like mud, okay, the wave goes through water, suddenly it goes through mud, it will change its speed. Okay, so can waves refract? Turns out they can also refract. They can change, when they change their speed, they change their direction as well. Okay, Zach has asked the 100,000 euro question. Are these separate theories or are they connected? Yes and yes, Zach. They're separate theories, and somebody found a connection as well. We're going to probably get to the connection, Zach, next time, but let's work a little bit more on the wave theory for now. Okay, I'm gonna jump, because we have just a couple minutes left. I'm gonna jump to the parts of the theory we really need to have in front of us. Okay. Okay, so now here's a wave. Oh, sorry, here's a wave. Wave. Okay, what could account for colors under this theory? What could account for colors? What do you think? And I'm going to look at my notes and make sure I draw it correctly this year. Oh, I didn't draw it last year. Well, flipping A. Yeah, I got to think about it then. So that's got to be like that, and then that's got to be. What do you think? What could change? What could I change about a wave that might give different colors? About a transverse wave, I could change the Yeah, great, Zach and Ellie. The wavelength, exactly. So, for an example, now you guys are hot. I love it. For an example, if I have a blue wave, it might look like this. But if I have a red wave, it's going to look more like this. In other words, blue, well, red has a longer wavelength. Longer wavelength. If you remember our little lambda symbol, lambda for wavelength. And blue is going to be a shorter wavelength. Shorter wavelength. Good. Last part of the theory, let me erase a little bit. This will be a perfect spot to end our day, is what about light intensity? What do you suppose could change about a wave to make it more or less intense? So what accounts, and again, we're talking about in the wave theory, for different light intensities. So aside from the wavelength, what else could you change about a wave? The frequency, yes, Ellie, except the two are really related. If I change the frequency, if I make it more frequent, then I make it shorter. So frequency and wavelength are really kind of the same. In other words, red I could say is a less often frequent, and this is more frequent. This is a higher frequency and a lower frequency. But what else could account for intensity? What else could I change about a wave? See if you can guess. So not the frequency or wavelength, because we use that already for color. Well, let's kind of make this, I'm going to go, this is going to be a dim blue. And this is going to be an intense blue. And we'll see what we can change about the waves. Okay, here's the dim blue. You ready? But what could I change to make it intense? I could change this. I can change the wave height. So if it's intense, it's got a greater, what is that? Have we had that word yet? I can't remember. Starts with an A. A greater, greater, Okay, it's amplitude. Did we have amplitude yet? Have we had that word? If not, I'll define it next time. But does that ring a bell? Have we had the word amplitude, folks? Yes, yes, or no, no? I think we did. Thank you, Teresa. Okay, then next time we're going to play Connect the Theories and find out who did it. And thanks, Zach, for that great lead in. So we'll see you later in the week. You know it from calculus. That's true. It's in math class as well, that word amplitude. Beautiful. Good. I sent you the BAT assignment, so ask me questions if you want later in the week when we meet. Okay. I won't meet you Thursday. So when do I meet you? Tomorrow? I'm a little lost. Anyway, As soon as I meet you again, we can take any questions on the BAT assignment if you have some as well. Okay? Don't want to drive you batty. Ah! Okay, so see you later in the week, and then we'll do a little on connecting the theories. Stay healthy, everybody.